name's Jeffrey Taylor. I'm here with Don Weiss. This is one of the dialogues of scientific materialism. And I do want to stress at the beginning, the whole idea for looking at the science here that we're going to do is to better integrate what science is learning with topics in philosophy and topics in religion. So the end goal here is not necessarily just to learn the science, but to also see how that opens up new areas of conversations with other disciplines. So I'm going to share my screen here.
And I'm here to kibitz with you today, since I'm letting you take it.
I'm going to talk about today two experiments. And these two experiments, physics experiments, are fundamental in understanding how our world works and how we may not have complete knowledge of that. So we're starting here with the double slit experiment and another experiment done by Elaine Aspect on non-locality. The double slit experiment is probably the simplest, easy to understand experiment that highlights the weirdness and our incompleteness in understanding reality. It demonstrates how it was meant to demonstrate how light basically is either a particle or a wave. And it might be useful to look at this point. Particles are localized entities, and they have both a location and motion. Think of a marble. A marble can be sitting on the desktop, or it can be rolling or falling. But particles have a locality, and they are discrete in that they have boundaries.
They occupy a certain amount of space, but only that amount of space, and they stop at their edges, and they're over.
Exactly. And particles have been the obsession of physics for over 300 years, and there's a very good reason for that. Everything we interact with our senses is based on particles. But the other part of reality are fields or waves, and they're fundamentally different from particles. They do not have a point location. They are spread out through space, and some of them are spread out through the entire space of the universe. Fields can have a motion, but it's very different than particle motion. It's not discrete. It's motion that happens throughout the fields. More importantly, fields are a distributed universal property of space. They are not matter. They are forces or other things that are distributed, and they are a property of the space that we live in. And a lot of us aren't used to thinking about space as being a fundamental player in physics. We think about it as a stage where matter happens to be, and we measure the matter into space. But in quantum mechanics, the empty space is a player and has all these properties that we're going to look at here.
In other words, space is made up of fields.
That is exactly right. That's a good way of putting it. The double slit experiment was done by Thomas Young in 1801, so almost more than 200 years ago. And at the time, it was thought that light consisted of either waves or particles, and he wanted to find out whether it was a particle or a wave. What he found out was that light seems to be both a particle and a wave. Now, if you look at the two definitions we just talked about, that's a contradiction in terms. A particle can't be a wave, nor can a wave be a particle. They are physically different entities that are mutually exclusive. So this caused great consternation. Even worse, in 1927, Dawson and Davison and Germer did the same thing with electrons rather than light. So here is the basic experiment. You have a light source down here that's giving off light, whether it's particles or waves, and you have two slits that it can go through. If light is a particle, what would happen is the particles would go through the slits and hit the detector screen, and there would be two bright areas where the light went through the slits. That doesn't happen. I have no written out beside that because that's not what you see. What you see is over here, you see a periodicity of light and dark areas that are caused by what's called an interference fringe, which is light acting as a wave. There is absolutely no way that a particle could give you an interference fringe like this of light and dark.
But you're saying that particles are shot through the slits, and yet even though the particles go through one by one, they end up taking a wave-like pattern on the final screen.
That demonstrates interference of the wave.
Even though you've done it particle by particle by particle, you just sent it through that slit, or that slit. It shouldn't be this way. It shouldn't be that the final array shows a wave-like pattern, even though you know you've been shooting particles, so to speak.
It gets even more strange. Over here on the right are just two actual experimental examples. The one on the top is what you'd expect from a single slit. You get a bright area where the light goes through the slit. If you open up a second slit, you get this alternating pattern of light and darkness. Let's take a look at the experiment here. Basically, Young concluded that these particles have something of a wave about them. And the very act of observing a particle has a dramatic effect on its behavior. This is another big no-no in scientific materialism. The experimenter or observer should not have any impact on the experiment just by making a decision of how he's going to measure it. And this was another, not only is the wave-particle duality a problem, the fact that the experimenter appears to have some say in what actually physically happens is kind of a problem with the scientific materialistic worldview. So here's just an example of you're firing photons or particles of light through a double slit. If they were particles and not a wave, you'd get particles appearing where the slit was. The particles that are outside the slits bounce off, only the ones, it's like throwing tennis balls is the analogy used here. Throw tennis balls through an opening and see where they hit on the backstop in back of the openings. So this is what you'd expect if there were particles, but you never, ever get this. What you get is this interference pattern generated by waves. Now, these waves go through the slit, and you see it forms two different wavelets. If you've ever gone to a pond or a swimming pool and thrown two stones or two different things in a pool, you'll immediately notice that waves go out through 360 degrees around where the rocks entered the pond. And when those waves start to interact with each other, you'll see that they interfere. In other words, where there's a peak in the wave, of the two waves, it reinforces it and makes a brighter area. Where a peak meets a trough, there's no, they cancel each other out. Where two troughs line up, you get a dark area. So these lines on the detector here that you see, these three lines, they are where constructive interference occurs. This little line going out from the blue waves shows you how these two sets of wavelets interfere with each other and make this distinctive interference patterns from where the bright spots reinforce each other. Now, what this means is light is going through the slits as a wave. That's undisputed. It is waves that are going through the slits and not particles. But now you get to the detector, and now total weirdness happens. The detector detects only particles striking it. It does not detect any waves. So the photons have to go through the two slits as a wave, and then they have to strike the detector as particles because they are clearly particles when they hit the detector. So this causes a huge problem as to what are they? A wave is not a particle. Does it magically transform itself somehow? And it has caused a lot of consternation in physics
But
Uh,
as a layman, what I want to say is the strangeness of the situation. Listening to you is that you've shot particles in the first place, and then you know that you get particles at the end of the process. What's the strangeness, of course, is the interference pattern, which shows that there's wave-like behavior. So what I want to say is this. As your student, what I would want to say, I would want to raise my hand and say, what we have here are clearly particles in one sense. I mean, we've launched them as particles and we receive them as distinct pings as particles. But on the other hand, we see that they arrange themselves in a wave-like pattern so that we have wave-like behavior, but nonetheless we have particles. What's wrong with that?
and you're seeing this thing of an interference pattern being generated.
Right.
Uh,
Generated out of little particle hits. It's
exactly.
nonetheless true that at every hit is the hit of a particle. It's just that the shape taken by the array, it's as if, and here we get into ultimately, this gets into probability theory. It gets into the fact that each flip of a coin is a distinct event, but you can show that it forms 50% heads and 50% a very clear pattern emerges from the flipping of a coin if you do it enough times. Here too, it's that we see a field of, we know that it's got to fall somewhere in these dark areas, but each one nonetheless is an individual particulate event.
And notice even more, if you kind of notice after the image has formed here, this is a probabilistic distribution.
Yes.
In other words, it's kind of like there's a Gaussian curve. Like the peak is in the center where it's darkest, and then it kind of gets lighter out towards the side. Which means that not only are there particles hitting the detector, they're striking it in a probabilistic fashion.
Right, which even means that you're going to see some outliers. You're going to see ones that are not near the center.
Yes, and you can see one, right, kind of right there.
Right.
This again flies in the face of scientific materialism. Things are not probabilistic in scientific materialism. So to go back here to get this back. So people have struggled for almost 200 years with this. Niels Bohr basically found a way of resolving it. He said, don't think about what it means in terms of reality. Just crank the math out. The math works. We know it works. It has never failed. Don't try and figure out what it means in terms of the world and reality. It's just a mystery, and don't think about it. Well, telling a scientist not to think about something is kind of like poking them with a stick for certain people.
So to summarize this view, you're saying that the problem is that the material world seems to be waves on the one hand and it seems to be particles on the other hand. And here's this, I want to point this out. Here's the missing important step now, is that we have no way of understanding how these two things could both be true. They seem to contradict each other. And you're telling me that Niels Bohr says, don't worry about that. As long, yes, you treat it like a wave in a certain respect, and yes, you treat it like a particle, and yes, it's true, you can't figure out what you're saying or what you mean, but don't worry about the fact that you don't understand what you're saying. The mathematics works. Treating it the way we've worked it out works and that's where you get to this crank out your results. This is what you're saying about this.
More or less, that was the mindset. And the reason for that was Niels Bohr was unwilling to give up the tenets of scientific materialism. On the other hand, Einstein was more than willing to give up some of materialism. Bohr and Einstein had numerous confrontations over thought experiments in terms of what it meant. But the Copenhagen interpretation really is saying, just crank the numbers and don't think about it. But there were people that thought about it. And, how do I deal with a contradiction and a paradox? Something has to be wrong. The light is leaving the source as a particle. It goes through the slit as a wave, and it hits the detector as a particle. How is that transformation occurring? Because the two have drastically different properties. Well, one person said, well, maybe the photons somehow interfere with each other. In other words, they're always photons, they're never a wave, and they interfere with each other. The problem with that is they didn't experiment to check that out. Interference requires two or more things. Interference never happens from a single wave or a single particle. So what they did is you can take an electron gun or a photon gun, and you can literally shoot one particle at a time through the slit. And that's what they did. They literally had a source that literally sent one photon at a time through the system, and lo and behold, the same interference pattern was generated over time, which means that the particles were not interfering with each other. They were waves. So the other one is rather more unique and really shows how the quantum world defies common sense. They said, is it possible the photon somehow splits and goes through both slits as one, as kind of a wave, and then recombines on the other side of the screen as a single localized particle? In other words, somehow this photon knows that when it gets to the screen, there are two slits there, and it divides itself or something. They made an experiment to test that out. What they did is they put a detector on the slit, on both slits. I want to know which slit the particle is going through. I put a detector at the slit, and I detect that particle going through the slit. In other words, I'm trying to sneak a peek at what's happening. Well, when you do that, as soon as you turn the detector on, you get an interference pattern. In other words, the system knows you're trying to peek and won't let you. It is basic. That's being rather anthropomorphic about it. But when the detector makes it look like tennis balls going through. As soon as you turn the detector on, you get the pattern for two slits and not an interference pattern. As soon as you turn the detector at the slit off, you get an interference pattern. It's like the system knows what you're doing, and as soon as you try to sneak a peek, it won't let you. It goes back to being particles. What it means is every time you measure this, it's a particle. It's never a wave. Yet it's got to be a wave going through the slit. So this, both the probability aspect of this and the fact that you can't find anything like a wave going through the slit, no matter how close to the slit you try to measure, means you're back to it leaves the source as a particle, magically becomes a wave to go through the slits, and magically becomes a particle. Now, what gets even weirder is, photons and electrons electrons are what is generated, if you can remember back to your old picture tubes that were big and were made of glass and everything. At the back of that was an electron gun that basically shot out electrons in a line-like pattern very rapidly, and it excited phosphors on your TV screen. So they know how to shoot electrons and even single electrons at things. But more recent experiments have gotten even weirder. They've actually done experiments with atoms and molecules. That they've done it with molecules up to 2,000 atoms, which is a pretty darn big molecule. So what we're now saying is it leaves the source as a molecule, somehow turns into a wave to go through the slit, and becomes a molecule when it hits the screen. Now, you can kind of ignore something like a photon as doing something magical like that. But when we get to molecules, we're getting kind of into the macro world where matter shouldn't do that. How does this molecule become a wave to go through the slits? So this caused an incredible amount of consternation in the world of science. And one of the premier people to try and figure this out is a man by the name of David Bohm. He died in 1992. He was one of the most premier and eminent physicists of the mid-20th century. And he contributed many unorthodox ideas to quantum theory. And he also dabbled in neuropsychology and the philosophy of mind. But he came up with the fact we've got an observation problem. If you look at the picture here, it's an aquarium with a fish in it. And there's a camera, there are two cameras positioned at right angles to each other. And down at the bottom, you see a picture of the fish from that camera. And if you will look at the one on the left, it looks different from the fish on the right. If you take away all knowledge of the aquarium and what you know about it, and just look at the output from the two cameras, those don't look like the same thing. They look like two different things. So Bohm hypothesized that what we have here is a hidden world somewhere that we can't measure, and they look different. He called the one that we observe the explicate order, and he called the hidden one the implicate order. And basically, this implicate order we can't delve into with experiments. He called them hidden variables or hidden stuff that we had no way to measure. And it made sense, but most scientists were not happy that there's a hidden world that they can't measure. But what's really interesting is he called the implicate order enfolded. It was somehow enfolded that we couldn't measure it, but it was a deeper, more fundamental order of reality. And in contact with what we see with our senses is the explicate order, which is unfolded and observable. And it goes back to something very old, which is Plato's analogy of the cave. In other words, Plato had Socrates in one of his dialogues tell this story about there's a bunch of people in a cave with their backs to the wall, forced to look at the wall in front of them. There's behind the wall, there's all sorts of strange things going on. There's a fire, and there's these mysterious people that are marching these things in front of the fire that cast shadows on the wall.
By the way, since this is philosophy territory, let me say it was in the Republic that this occurs, and I would point out to anybody who might be watching this that what's also remarkable about it is that it's essentially a motion picture kind of scenario of throwing images, just the way a movie projector works, through throwing light through an image and casting an image therefore upon a screen in front of the viewers. So you imagine yourself in the seat in a theater, but you can't turn around. What you cannot do is turn around and see the source of the light. You can't turn around and look at the projector. In other words, these people were bound to their seats, and all they could see what was on the screen, in Plato's very, very wonderful analogy.
So Bohm really gave credit to Plato that he just reformulated his allegory of the cave, where what's happening on the right here with the shadows that everybody's watching is the explicate order that everybody sees, but now we have this wall, and what's hidden behind it are all the mechanisms of the implicate order. And most scientists at the time did not like the concept of a wall, keeping them from measuring something. Bohm was very widely respected, but he couldn't really quite sell this, but he really integrated it in other things like neuropsychology and things like that. He was a very innovative person that thought outside the box, and many of the things that he came up with are still applicable to the final solution that they found in quantum field theory. Quantum field theory goes back to the 1940s, 1950. And without getting involved, it's another way of doing the math. Quantum field theory comes up with the exact same answers as quantum mechanics, but the concept behind it is very different. It makes a statement about the world and integrates itself into how the world can work. But what it says, it has a very high intellectual price tag to pay, because quantum field theory says that fields are the primary component of the universe, not matter. Fields are properties of space, and they are primary. Matter is a derivative property of a field in space. In other words, matter is not primary. And scientists for the past hundreds of years have been pursuing matters and particles as what they measure. And Albert Einstein basically made the statement that fields are spooky action at a distance. It's like he referred to it as mysticism, that it's very, very strange. And for that to be the primary component of the universe was just too much for people to actually accept. But it's very consistent with other, actually, I'll bring in a religious component here. The Hindu religion 6,000 years ago was saying matter is an illusion, and what you're seeing are your senses interacting with energy fields. And that's exactly what's happening in quantum field theory that was first stated by Hindu philosophers 6,000 years ago. So what I'm trying to do here is give everybody an idea of these things are not separate fields of study that are independent from each other. Religion, philosophy, and science are all questing for the same type of thing. They're just doing it with different methods. So to finish up, we're back to the particle, as we said at the beginning, being a tiny, a localized object. And I have a quote here from Gary Zukov, who's a rather prestigious physicist, who says, according to quantum field theory, fields alone are real. They are the substance of the universe, not matter. Matter is simply the momentary manifestation of interacting fields, which, intangible and insubstantial as they are the only real things in the universe. He's saying what the Hindus said, matter is not real, it's an illusion. What's real are the fields behind it. Now, quantum field theory has two different types of fields. Attached fields, which are static. These are your force fields, gravitation, the electromagnetic fields. These fields can't go anywhere by themselves. There are then separate fields that are not attached that are matter fields, and they may spread over great distances, but they live and die as a unit. So I just...
You mean a photon, for example?
A photon is a different field. Well, no, that's not true. A photon is a matter field. As you'll see down here, these are the 6 fields that we know about today. There's gravity, the electromagnetic, the strong nuclear force, and the weak nuclear force. Everybody's familiar with gravity. One of the reasons Newton struggled with his gravity equations because he was greatly distressed by how does the Earth exert an influence on the moon when they're separated by such a tremendous difference. So he was the first to voice the spooky action at a distance that Einstein later repeated. Everybody's familiar with the electromagnetic force, which is light and magnetism. The strong nuclear force holds the nucleons in the atom together. It's what holds protons and neutrons in the nucleus together. And it's actually quite a strong force. The weak nuclear force is what causes radioactive decay. We'll just say that these two, the strong and the weak nuclear force, exhibit themselves only in the realm of the atom, whereas gravity and the electromagnetic force are very visible to us. The matter fields come in 2 varieties. Leptons are light particles, photons, electrons, neutrinos. All these light particles are called leptons, and they have a separate field from the baryons. The baryons are the heavy particles, protons, neutrons, other large particles, and there are 2 separate fields that address each. But the take-home message in all of this is it's been very difficult for physicists to accept force fields as having a real existence. But quantum field theory mathematically processes all these fields and gives the exact same data as quantum mechanics. It's the philosophical implications of what quantum field theory says that is what makes people or scientists want to avoid it. Because it's saying the solid stuff that we all know is not primary. It doesn't really have a real existence. It's a derivative property of a field. So one last thing here. One other experiment. And this one is a tough one, but it's significant and I wanted to go over it, but it's not terribly easy to understand. But what it is there's this property in quantum mechanics called entanglement. And it means if you create two particles from something, these two particles are entangled. In other words, they are linked to each other across space. And basically what it means is every particle in the universe is entangled because they all derived during the Big Bang, and everything in the universe is then entangled. And basically Einstein, Podolsky, and Rosen came up with a paradox that they were arguing with Bohr over non-locality, because the quantum world appears to be non-local. And I'll get to what that means in just a second. But back in 1980, Alain Aspect did an experiment that finally proved Albert Einstein, Podolsky, and Rosen were correct and Bohr was wrong. The whole world is entangled. And entanglement was derived from Erwin Schrödinger in 1935. And he's the one that said that once two separate quantum systems that have been interacting with each other and come from a common origin, they cannot be considered as two independent systems. So Aspect's experiment was based around something called Bell's inequalities, which was a statistical model of how you might prove non-locality. And I don't want to get into it, but what his experiment proved was all of quantum physics is non-local. The principle of locality is like, where are you at on Google's maps? You're occupying a fixed space, and you have things that are around you that are local to that space. Right now, I'm sitting in my office, and what's local to me is I've got a bookshelf over here and other things. And locality is where an object is directly influenced by the immediate surroundings. In other words, I turn on the light in my office, and I can measure that. Don, who's sitting out on the extreme eastern end of Long Island, would not be able to see my light. So what my local light does not, nor can Don measure my local light. And non-locality says that location is an illusion. What's really happening is action at a distance. And non-locality evolved out of field theory. But in order to exert an influence, something such as a wave or particle must travel through the space between 2 points carrying the influence. In other words, if two particles are going to quote unquote communicate, they can't do it faster than light, because the speed of light is the total speed limit for all particles. So what they actually did in the experiment, and this is very simplified. Here on the left, you have two entangled particles. We'll call them Bob and Alice. And you do something now that they move away from each other. They were generated by the same system. We'll say Bob and Alice were born from the same mother, so they're entangled. But now we can measure the properties of Alice and the properties of Bob by something called, it's a quantum number called spin. What it means is two different particles that are entangled, when they're measured, if you measure one particle as being up, the other particle must be down. You can't come up with two Bobs or two Alices when you measure them. If you measure and find out it's Bob, the other person has to be Alice by default. So when we measure Alice, basically, we know that the other one is Bob. Once we know one of them, we know both. That's information that we can derive simply by the fact that we've measured one. But what happens now if we separate these two particles to a distance that is greater than the speed of light can communicate before we make our measurement? And that's exactly what the Elaine aspect experiment was. He basically measured two parts generated in a linear fashion in opposite directions and let them get far enough apart that they couldn't communicate by the speed of light. And he measured and found that one was Alice and the other one instantaneously became Bob, even though there was no way that what happened to Alice could be communicated back to Bob by any type of particle or anything like that. And this is the problem of non-locality. This is the actual experiment here on the left, and I don't want to dwell on it. It was actually using polarization, and it separated this distance large enough to when you measure measurements, these two detectors could not communicate faster than the speed of light. And what it amounted to is it proved that they could. They've now done his experiment over, it's been 30 years, and they've used even things again, not just the properties of small particles. They've actually done this experiment with molecules again, and the same is true. What this means philosophically is that the entire universe is connected by a field where information can be exchanged instantaneously, because information moving through a field does not have to follow the speed of light. Basically, we can measurement on Earth, and if it's got a companion particle halfway across the universe, that particle will know what happened to the other particle.
Let me interrupt now with a question, because I want to try to model this, as I would call it, in my own mind. What I mean is come up with a model for understanding what you're saying. Suppose I want to pick up on a certain way of looking at things. What you seem to be saying is that although two things are separated by a vast amount of space, too much space to be traversed in time for information to get through, because it would be because it's instantaneous, rather than taking, light takes a while, it takes 9 minutes. For if the sun were to be blotted out right now, we wouldn't know it for 9 minutes. The information wouldn't reach us for 9 minutes, because it takes light that long. And in fact, light, although it seems very fast to us by ordinary human standards, actually is agonizingly slow when you talk about the billions of years that it sometimes takes light to reach us from very, very distant astronomical objects. But it creates to me what you're saying now when you say that two spatially very distant, maybe light years apart events are connected instantaneously. It suggests the language of saying that although on the surface of things they are spatially different, underneath the surface, in some beneath the surface sense, they are right next to each other. They are not, in the ordinary sense of space, they're not right next to each other. We admit that. But there's another sense in which we have absolute proximity to one another in an informational sense, or whatever it might be. Now, here's a model that it strikes me as recommending itself at this moment. It seems to me that suppose we have a tree on a flat surface, on a plane, an ordinary plane, an oak tree growing, and over here, a mile away or 100 yards away, let's say, is another tree, okay, a similar kind of tree. And we notice that the tree, that when you do something to one tree, it seems to have an immediate effect on the other tree. And then later on, we discover that beneath the surface, that's the level ground, they come out of a single root system. What we actually have are two different plants growing out of a single root system. Now, is something like this the model that we should start to think about, that although the trees appear to be spatially separate, and this is just a model now, I'm not saying that we should use this model ruthlessly, that it could be applied, but beyond an elementary level. But nonetheless, it gives us a way of understanding language that says that although apparently two things are spatially separate, they can at root be one with each other. is that a fair model to adopt?
Yes, it leans a little on the, I guess I'm trying to, while you were talking there, I was trying to think of a way. Do you remember when you were little and people told you that God is everywhere?
Hmm.
He sees everything, he knows everything in the entire universe. Science would define God as a field. A field, because of its non locality, is subject to communication with everything in the universe instantaneously. Your analogy is a good one between the two trees, and there's something hidden underneath that connects them. What's underneath connecting them is a field. And that's the struggle that most people have with field theories is we're now reaching the realm where we're talking about the universe being totally interconnected, basically with information. And there is no barrier to the information transfer because it's going through the field. We'll do another short dialogue here at some point in time where this will make a little bit more sense when we actually understand how a quantum field actually works. And that will make a little bit better analogy than the two trees, although it's good. But what's connecting the two trees underneath, the two trees are particles, and what's connecting them underneath is the field.
Right, and I have questions about fields. By the way, you can interrupt this whenever you want, but is it the ocean is a field, is it not?
Uh, that's often the analogy that is used. Uh, it's limited in the ocean, but all parts of the ocean are in communication with each other. You can think of the waves at the top as being particles being generated. Yet this field underlies everything, and the ocean it's
And
not a great analogy, but it works for a lot of people.
but theoretically, does instantaneous coordination occur in the ocean as well? In other words, if there's a change in the value of a force field, this is right here. If there's a change in the ocean right here, is there an instantaneously compensating change everywhere else within the field?
Uh, That's a little hard to answer. I'm not quite sure how to answer that. It's learning
I'm
to.
trying to think of fields at all. I'm trying to think of how do fields behave? What is it to be a field? And isn't it to say that a change in one location also, I mean, for example, I think of the wave function also, um, that each part of the field actually is in communication with all other parts of the field.
Yeah, I mean, the word communication is a word we use to get it. It's not really communication. They're an integral part of the same thing.
Correlation then.
We're so used to thinking about matter that it becomes very difficult to think in terms of fields because fields literally they're a property of space. So basically, you're dealing with the fact that space is a total interconnected whole that just knows what's going on everywhere, is the only way I could put it.
Mhm.
But that's so foreign to the way I mean, you think about all the things, even back to the 1900s. Science is obsessed with particles.
Yeah, but wait, I've got to break in. Einstein was in pursuit of a unified field theory. He hoped that all the fields of physics could be reduced to a single underlying field. He failed in his quest in his own lifetime, but it was his dream, and the dream itself lives on, even though Einstein doesn't in some sense. So now, remembering all of that, and remember what you said about God being everywhere, if there were such a thing as a unified field embracing all things, that would be God is everywhere, would it not? That would,
Yes,
okay.
yes, and it's
And it has to
uh,
be. Isn't it true? I have to press you now as a scientist. Isn't it true that science will never get out of its head the urge to unify? That is, when you showed those four fundamental forces before, one wanted to add the qualification that since the 1960s, Steven Weinberg comes to mind and so forth. She was at Sheldon Glashow also, who were involved in, and Salam, who were involved in showing that at a certain level, you could unify the electromagnetic field with the weak nuclear force so that we moved in some sense down to three fundamental forces viewed in that way. And the quest is still on to show that the other three forces could have some, and Hawking, Stephen Hawking, was hopeful that there could be a reduction of the fields into one super field that would explain everything. And my question to you is, isn't it true that science, by being scientific, is always trying to achieve that kind of unification?
Yes, and it is because the basis of trying to come up with what's unified is to unify all the particle generation. It was something that revolved around particles. If you look at quantum field theories, all six of the fields that we know are unified because they're all properties of space. There's nothing more you can do with them. They're already, all six of them, fundamental to space. The idea of a field being a property of space makes unification irrelevant.
Mm-hmm.
They are all unified. It doesn't speak now. The other thing that scientists are concerned about is this idea of fields being primary now opens up the door to other types of fields that maybe we don't know about. Is there a field associated with the human mind that interacts with these six other fields? It now brings, rather than research being solely restricted to the universe and space that we see, we now have to bring in the human mind and consciousness as part of possibly a field that's fundamental to interact with this. So, what types of fields are out there that we don't know about because we've been obsessed with particles for so long? It really opens up the avenues of discussing what the mind does, neuropsychology, all sorts of things that perhaps the next great advance will be through people meditating in brain study as to how we are part of the same system. We're in space. You can't separate us from that. So if there are any fields associated with consciousness or the human mind, those would have to be taken into account.
I would take it that it's here that you would link back to your fascinating discussion of the placebo effect, the possibility that a field of mind that we actually do participate in actually interacts with other fields, normally termed physical fields, having to do with biological function, for example, and that this would explain the placebo effect, that there is an actual field that does interact with another field. Is that on the right track?
That's a perfect example. I wasn't thinking about that, but yes, you're talking about a belief in the mind altering physical reality and manifesting symptoms or an effect in your body that mimics the effect of the drug. So it basically means your mind is actually able to interact with the fields and manipulate matter fields.
As a matter of fact, Jeff, if I were to make a suggestion at this point, you don't have to act on it. We can go as we want with the flow. But it seems to me at this point, it might be a very, very good thing for you to make a presentation on why you think the placebo effect is of overwhelming significance. I mean, there are such a thing as not necessarily crucial experiments, but crucial thought experiments, crucial ideas, crucial moments, crucial models, or examples. And I think that in your repertoire, we all have them. We teachers have them. We have a rap that we might, well, a sermon that we want to deliver on a certain kind of subject. But one of your most fascinating ones has to do with the fact that the placebo effect is much more significant, amazing as it already is. It is much more significant than it at first appears, and shows us that something really wacko is going on at the foundations of what we normally think of as standard reality.
Well, it's interesting that we were talking about some things, but that science's response to something that they don't understand or haven't figured out yet is usually to ignore it. But they'll fundamentally use it. The placebo effect is a good example. You do a drug trial. That drug trial has to prove the drug is safe and effective. So they developed a procedure that the person who's giving you the drug doesn't know whether they're giving you the drug or the placebo, because they don't want any inadvertent subliminal communications done from the person giving you whatever. So in a double-blind study, the person who's getting it as well as the person who's giving the drug doesn't know. But in all of these studies, there is a significant percentage of people that got the placebo that manifested the effects of the drug. An example, someone gives you something and says, this is a Motrin, you have a headache, and your headache goes away. The placebo effect is so prevalent, every single clinical study not only has to have a placebo in it, but they have to statistically correct for the placebo effect. There hasn't been a study where there was no placebo effect. So they have to generate statistics that is the effect of the people that got the drug statistically significant if you take away the people that got the placebo and manifested the effects of the drug. Philosophically, what that says is the placebo effect and the fact that they have to include it in every single clinical trial is saying that people, through their belief, are able to manifest things in their body that mimic the drug.
And let's be clear about this. It doesn't just mean, for example, that they claim that they feel better. It means that their blood pressure or whatever it is that you're studying at the moment actually does show these changes based upon belief. Objective measures actually do show these changes, not just subjective reports.
Yeah, you're talking about people with tumors that have gone away or gone into remission, physiological changes, like you mentioned, blood pressure, things like that. It's amazing when you think about it. But again, like the Copenhagen interpretation, I don't understand how that can be, but I've got to address it, because otherwise we won't have a successful clinical trial, because we won't know if the medicine was actually effective until we account for the placebo. So we use it in every single clinical trial, but walk up to a doctor and say, that person cured themselves by believing it. That they won't accept. Yet the placebo effect clearly demonstrates something's going on.
Yeah, and so it becomes an example of overwhelming.